Yeah, so today we are going to start with Fermat's little theorem. And why I was saying that there's another big theorem, is Fermat's last theorem, which actually says that a to the power n plus b to the power n equal to c to the power n has no solution in non-zero integers for n strictly bigger than 2. In fact, Fermat wrote in the margin of his book of, this copy of Diophantus book, Arithmetica by Diophantus, that this margin is too small to write the proof, but actually people do not believe he actually found a correct proof of that statement, and it took almost 350 years to solve that problem. So that is Fermat's last theorem. But this is Fermat's little theorem. It is to do with congruences. And what does it say? Let's take P to be any prime number and A to be an integer co-prime to P. In other words, suppose A is not divisible by P. Then A to the power P minus 1 is congruent to 1 mod P. Okay, that's all it says. For example, let's take the prime 5. So if we look at, of course, 1 is co-prime to 5 and 1 to the power 4 is 1 mod 5, that is clear. But if I look at 2 to the power 4 is 16, and 16 minus 1 is also divisible by 5. If I take 3 to the power 4, 81. 81 minus 1 is also divisible by 5. And if I take 4 to the power 4, this is 256. That is also, if you subtract 1, is divisible by 5. So it is certainly true for 5. We can directly verify. But in fact, it is true for any prime. So we'll prove this, and we also have to bear in mind that there is a generalization to composite numbers. Okay, there's a generalization to composite numbers, which is known as Euler's theorem. We'll come to that next week. Okay, Euler's theorem. So our proof, this particular theorem can be proved in many different ways, but we'll prove in a way that can be easily generalized to composite numbers. Of course, we'll have to modify the statement. Like if I take a composite number, let's say 6. Okay, so you don't expect, say, 5 to the power 5 is congruent to 1 mod 6. It may or may not happen. Okay, so we have to modify the statement. Okay. So in fact, 5 to the power, so if I take a composite number, say let's say 6, then you can see that 5 is co-prime to 6, but 5 to the power 5, it is like 5 square times 5 square times 5. 5 square is like 25, which is 1 mod 6. So it's like 1 times 1 times 5. So you can clearly see that 5 to the power 6 minus 1 is congruent to 5 mod 6, and it's not 1 mod 6. So certainly we have to modify the statement for composite numbers. But for prime numbers, it is certainly holds. Okay, and for composite number, we'll have Euler's theorem. We'll have to, in fact, we have to recognize this exponent as not 1 less than this modulus, but in fact, we should interpret as the number of positive integers less than p and co-prime to it. That's the right way to generalize. Okay, as I said, we'll generalize this later. We don't interpret this exponent as just 1 less than this modulus, but in fact, if we take it to be the number of positive integers less than this modulus and co-prime to it, that will be the right generalization. Otherwise, obviously, we'll start into difficulty, like 5 to the power 5 is not 1 mod 6. Okay, let's see how we prove this. Okay, let's take the first p minus 1 positive multiples of a. So let's take a, 2a up to p minus 1a. Okay, how many numbers are there? There are exactly p minus 1. Okay, and we'll claim that, and all of them. So let's see. We'll have to see that no two of them are congruent. Like if I take 2a and 5a, for example, suppose my prime is, let's say, 7. So we should be able to show that 2a and 5a are distinct, or 2a and 6a are distinct, mod p. This 2a and 6a should be distinct mod 6. Okay, so let me just check whether there's any query from anyone. Okay, there seems to be a query. Okay, no. Yeah. Okay, so how do I show this? That these numbers are pairwise incongruent modulo p. Okay, which basically, for example, if I take the prime 7, it will mean that this 2a and 3a, or 2a and 4a, or 2a and 5a, or 2a and 6a, or 2a and a, they are incongruent. So if I subtract, we will not get a multiple of 7. Why? Because suppose they are congruent. Suppose to the contrary, that IA is congruent to JA mod P. What are these I and J? They runs from 1 to P minus 1. And suppose one of them is strictly bigger than the other, because if they are not equal, if I and J are not equal, one of them will be certainly bigger than the other, strictly bigger. So we want to rule this out. Okay. So suppose we have this. Then clearly what will be J minus I? You subtract the smaller one from the bigger one. Then still it will be less than P minus 1 and bigger than 1. Okay. Because it will still be in this range only. But if IA is A mod P, I can cancel A, because GCD of P and A is 1. Because remember, in this statement, A is something coprime to P. So I can cancel A, and I get IJ are congruent mod P. Okay. But that will be a problematic, because that means J minus I is divisible by P. So J minus I is divisible by P will mean that J minus I should be 0 or P or 2P, etc. Already we know that I and J are not equal, so it is not 0. But J minus I cannot be P also, because it is strictly less than P minus 1. So in other words, this cannot happen, that if I is not equal to J, IA would be congruent to JA, when my I and J runs from 1 to P minus 1. So that means they're all distinct mod P. Okay, they're all distinct mod P. Okay, so what is the advantage of that? What is the advantage of these numbers being incongruent mod P? Because they are P minus 1 of them. So that will mean that when I divide by P, their remainders will cover from 0 to P 1 to P minus 1, not 0, because P does not divide A. Okay. So when I divide these numbers by P, I'll get 1, 2 up to P minus 1, not necessarily in this order. Here maybe dividing by A, maybe I'll get 3. Dividing 2A, I might get 1. Dividing P minus 1 times A, I might get 5 or something. But what I'll be getting as remainders will be this 1, 2 up to P minus 1. So when I divide, so mod P, these numbers are nothing but these. Okay. Or in other terminology, we say that they are both reduced residue systems. Okay. That both are reduced residue systems. We defined it last time, but even if we have forgotten the definition, does not matter. All we are saying is that these P minus 1 numbers, they leave different remainders when divided by P. And none of those remainders could be 0, because P is coprime to A, and P is also coprime to these coefficients. Okay, because we are going up to 1 to P minus 1 only. So the remainders will be from this set. So that means when I multiply, if I multiply, then that will be equal to this product mod P. Okay, so if we take all the elements in this set and look at the remainder when divided by P, it will be same as the remainder when we multiply these numbers and divide by P. Okay, in other words, I mean, we know that X is, suppose X is X congruent to Y mod P and Z congruent to W mod P, then we know that XZ is YW. mod P. So if individually the factors satisfy a mod condition, like suppose individually, let's say x1 is congruent to x2 mod P. I mean, sorry, x1 is congruent to y1 mod P, x2 is congruent to y2 mod P. Then x1, y1, x2 is congruent to y1, y2. So all that we are saying. So if we take this product from this first set and we take this remainder set and we multiply, they will be same. They will be equivalent mod P, because each one is A. For example, it will correspond to some remainder. Let's say 2. Suppose 2A, it may correspond to remainder P minus 1. Okay, but overall it will not matter. When you take the product, it will not matter. I mean, which remainder is what, because overall there's okay. But then what happens? These we are getting a to the power P minus 1 and then P minus 1 factorial. Okay, and on this side I'm getting P minus 1 factorial. And what is the good thing about P minus 1 factorial? It is co-prime to P, because it's product of all integers less than P, strictly less than P. So when GCD of this coefficient and these modulus are co-prime, it can be cancelled off. And I get this. Okay, so that's how we prove Fermat's little theorem. Okay, any questions so far? Let me know if we have any doubt or any query.
Hello, sir.
Yes.
Sir, P and P minus 1 factorial would only be co-prime if P is not I think this statement, well, I didn't understand the statement why GCD of P and P minus 1 factorial would be 1.
Okay, so let's say P to be 5. Then yes, P minus 1 factorial is 4 factorial. So its elements are 1, 2, 3, 4. Each of them is co-prime to 5, because P does not divide anything less than it. Okay, P does not divide anything from 1 to P minus 1.
Yes,
so
sir.
P will not divide their product.
Yes, sir.
Okay?
But suppose, sir, if P is 6, then P minus 1 factorial will also have 2 waves.
Then you have to look at
P is a prime number.
It's a prime number. Huh? Okay, that's why we said it is P. It's a prime number. Okay.
Yes.
Yeah. And okay, so in fact, one can use induction to prove this, and binomial theorem also. Other ways to do this, but this is the proof we are doing, because it will be almost exactly the same argument for Euler's theorem when we do it for composite number with a modified statement. Okay, so let's Fermat's little theorem. And corollary. Okay, you take any prime number and any integer, forget coprimality. So P may divide A also. Then you will always have A to the power P is congruent to A mod P. Okay. Sometimes this form is also referred to as Fermat's little theorem. Okay. But they are almost equivalent. Okay. We are saying because of Euler's theorem, basically we are giving the statement like this. Okay. That is the main statement. This is a easy corollary, because if P divides A, see, there are only two cases, P divides A or P does not divide A. If P divides A, clearly this is 0 mod P and this is 0 mod P. So it's clearly equal. Okay. If P divides A, he will also divide any power of A, positive power. Okay. So it's clear. And if P does not divide, already we proved Fermat's little theorem. So I will multiply both sides by A and I'll get the desired result. Okay, I'll multiply both sides by A and I'll get this. Okay. And when A is coprime, I can cancel A, because if from this statement also I can go back to the other one, because when A is not coprime, I can cancel this A and this one A from here. So I get this. Okay. So I can go back and forth here. So I can call this theorem and the other one corollary, but it's better to stick to the version that we had. Okay. So how does it help? For example, I want to compute a big modulus. Okay, modulo some prime. When we have Euler's theorem, we can handle composite numbers also. But since we are demanding our modulus to be prime, for the Fermat's little theorem. So let's just do this. Then what we have to observe is that since 9 and 11 are co-prime, 9 to the power 10 is 1 mod 11. Okay. So if I raise it to this big power, I'll involve this 10 because this will give me just 1. 9 to the power 10 mod 11 is just 1. And I'll be left with just some 9 square, which I can directly compute as 81 and evaluate. But just to give you an idea, I can cut it down further because 9 is congruent to minus 2 mod 11. So this computation is even simpler. Of course, for this kind of small numbers, it doesn't matter. But imagine if we have very big numbers. Suppose it's a 100-digit prime, and this is like some 200-digit. Whatever big number, then we can always cut it down, okay, and reduce the arithmetic. So the remainder is 4. Okay, so that's how it is useful. Okay, that is Fermat's little theorem. Okay, now it may happen that some composite number also may exhibit this behavior. That it may be that 2 to the power n minus 1 is 1 mod n, but that it will not actually imply n is necessarily prime. Okay. First of all, anyway, even if it happens not just for 2, even for all any a co-prime to n, even if then also, in fact, it need not be prime. Okay. Because see, this type of behavior is certainly true for prime numbers. Okay, so it's a necessary condition. If n is a prime number, this is necessarily true, but this is not sufficient. Okay, that this will not imply n to be prime, and we'll see some counterexamples. That's why they're called pseudoprime. So what is a pseudoprime? It's not a prime, it's actually a composite number. It's a composite number, but when it behaves like a prime number when we look like this. Okay, and some books refer to it as Fermat pseudoprime also. Okay, sometimes this terminology is also used. Okay, and we are sticking to the notation in Niven, Zuckerman, and Montgomery. Okay, because in Barton's book, it's slightly modified version is given, but it's better to stick to this. Okay, because in the Barton's book, it will be given as 2 to the power n congruent to 2 mod n. That is a pseudoprime. Okay, and there are some reasons why that way it is done. Because classically, some mathematicians looked for prime numbers among the integers of the form 2 to the power n minus 2. Okay, and it was believed that 2 to the power n minus 2 to the power n minus 2 factors of that will give you prime numbers, kind of. Okay, that hope was there. But yeah, so this is our, why you're calling it a pseudo prime, because had P been a prime, certainly this should be true. Okay? Because by Fermat's little theorem, if I have an odd prime P, certainly this will be true by Fermat's theorem. So certainly it is necessary for a prime number, but this is not sufficient. Okay? So the behavior of a pseudo prime resembles that of an odd prime, but actually it is not a prime. Okay? For example, let's take this 341. It's a pseudo prime. Okay. Why? First of all, it's a composite number because it is 11 times 31. Okay. But if we'll see that if we raise it to 3 to the power 340, we'll have to check that 2 to the power 340 is 1 mod 341. That's what we have to verify. Then it will qualify as pseudo prime. Okay. So, but we cannot apply Fermat's little theorem to 341 because already we know that it is factorizable like this. So we look at its prime factors. We know that 2 to the power 10 is 1 mod 11 and 2 to the power 30 is 1 mod 31 because this is 1 less than this prime, it's 1 less than this prime. Okay, and the good thing is if we look at 2 to the power 340, I can write as 10 to the power 34, and I know that 2 to the power 10 is 1 mod 11. So this is just 1 to the power 34, which is 1 mod 11. Similarly, so 234 minus 1 is divisible by 11. Similarly, 2 to the power 340, I now break it up as 13 to 11 times to the power 10. Okay, 330 plus 10, 340. But okay, yeah. So this 2 to the power 30 is 1. So it's 1 to the power 11 is already gone. Okay, this is like 1. And now this 2 to the power 10, I can evaluate in different ways. But best thing to observe is that 2 to the power 5 is 32. And 32 is 1 mod. Oh, by the way, this is 31. Okay, anyway, it's clear. This is 31, 31. This is 30. So 2 to the power 5 is 1 mod 31. So it is 1 square mod 31. So it is 1. Okay. So in other words, 2 to the power 340 minus 1 is divisible by 11 and 31. And hence it will be divisible by their product. Because these are co-prime integers. I mean, think of its factorization. 2 to the power 340 minus 1. It has a factor 11 and it has a factor 31. So it will have a factor 11 times 31 because they are co-prime. Had it been 11 and had it been 11 square, then you cannot say that it will be divisible by 11 cube, certainly. Okay. Because 11 square itself is an example. 11 square is divisible by 11 and 11 square. So it's not divisible by 11 times 11 square. But important thing is these are co-prime. So this will always be true. So it's a pseudo-prime. Okay. And sometimes, see, this is only 2 was involved. So sometimes this terminology is pharma pseudo-prime, and some people say pseudo-prime to the base 2. Okay, because it is 2 that we are exponentiating. So we may consider some other base also. Okay, so then we'll get pseudo-prime to the base A. Okay, that is what we're going to. Okay, before that, we'll have to. So it's a natural question, whether there are infinitely many pseudo-primes. We already know that there are infinitely many prime numbers. Okay, so the question is, will there be infinitely many pseudo-prime? And that is easy to prove. Okay, because one pseudo-prime will give a next one. Okay, if n is a pseudo-prime, then 2 to the power n minus 1 is also a pseudo-prime. And certainly this will be bigger than n. Okay. So that way, then next time you start with mn and you get another one. Okay. So you can keep producing pseudo-primes. How do I know that this is pseudo-prime? First of all, n is composite because it is a pseudo-prime. So actually it is a composite number. So I can factorize it as r times s, where s is strictly less than n. Okay, these factors are strictly between 1 and n. So that is composite number. Then what can I say? Then I can easily see that 2 to the power r minus 1 will divide 2 to the power r to the power s minus 1. Okay, because you know that x minus 1 divides x to the power s minus 1. It's like that argument. Okay, let 2 to the power r be x. So this is x minus 1. And it is x to the power s minus 1. Because x to the power s minus 1, I can write as x minus 1 times x to the power s minus 1 plus x to the power s minus 2 plus up to 1. Okay, so certainly this is a factor of this. So that means 2 to the power r minus 1 divides mn. Okay, and 2 to the power r minus 1 is strictly less than mn because r is strictly less than n. And why we are doing this? To show that this is actually a composite number. Okay, so to qualify as a pseudo-prime, first of all, it should be composite. Okay, that we have verified. And we have used the fact that this is composite, so that is also composite. Now we have to show that 2 to the power, we have to look at 2 to the power mn minus 1. What happens to that? Okay, so we'll have to look at that. And anyway, these things, it's best to work it out yourselves. Okay, then you can see how these arguments carry on. Okay, so anyway, so I'm giving the argument. So we have this property because anyway, at some point of time we have to use the fact that n is a pseudo-prime to the base 2 or is a pseudo-prime. So this is the property that we have. So I can multiply both sides by 2 and I'll get 2 to the power n minus 2 as a multiple of n. It is basically telling us this, that 2 to the power n minus 2 is a multiple of this. Okay. So if we look at, but what is 2 to the power n minus 2? It is mn minus 1. Because why we are looking at this? Because we need to look at mn minus 1. What is mn minus 1? This 2 to the power n minus 2. And what can we say about 2 to the power n minus 2? It is a multiple of n. Why? Because n is a pseudoprime. Okay. So let's look at 2 to the power mn minus 1. It is 2 to the power 2 to the power n minus 2. But I know that this is a multiple of n. So it is 2 to the power kn. Okay. So what will I get? I'll subtract 1 from both sides, and we can easily see that again 2 to the power n, if I think of it as x, so it is like x to the power k minus 1, which I'm factorizing as x minus 1 times x to the power k minus 1 plus x to the power k minus 2 plus dot 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 plus x plus 1. Okay, and whatever it is, we don't bother about that, but this 2n minus 1 is mn. So basically it is 0 mod mn. Okay, because this 2n minus 1, it is our mn, and it is some integer. It is some integer. So 2 to the power mn minus 1 is 0 mod mn. In other words, 2 to the power mn minus 1 is congruent mod mn. As I said, you just work it out so that we can produce one pseudoprime after another one. Okay, so there are infinitely many pseudoprimes. Okay. Any question? Okay, suppose there are no questions. There are infinitely many pseudoprimes. Okay, so so a composite integer is called pseudoprime to the base a if a to the power n minus 1 is congruent to 1 mod n. Okay, I mean, okay, so this heading is misleading. Okay, so I got confused myself. But what we are saying is that pseudoprime to the base a. Earlier we talked about pseudoprime to the base 2, so to speak. If we use this terminology, we earlier talked about pseudoprime to the base 2. So now we are saying that if a to the power n minus 1 is congruent to 1 mod n, so we'll say that n is a pseudoprime to the base a, that particular a. Okay, but when we are taking base 2, we don't even refer. By default, base is 2. Okay, and if it is any other base, we specify it. Okay. So for example, 91 is a pseudoprime to the base 3. Okay. And one can show that it is the smallest pseudoprime to the base 3. So what will be required? That 3 to the power 90 should be 1 mod 91. Okay. And 91 is 7 times 13. Okay. What it will require? 3 to the power 90 should be congruent to 1 mod 7 and 1 mod 13. Okay. And by Fermat's little theorem, 3 to the power 6 is 1 mod 7. So certainly, and 6 into 15 is 90. So you know that 3 to the power 90 will be certainly congruent to 1 mod 7. You can just compute. What about 13? You know that 3 to the power 12 is congruent to 1 mod 13. Okay. So we have to go 3 to the power 12. So to reach 90, we can raise it to power 7. Okay. So 7 times 12 is 84. So if 3 to the power 12 is 1 mod 13, 3 to the power 84 is also 1 mod 13. So what remains is 84 plus 6. So we have to check that 3 to the power 6 is 1 mod 13. So 3 to the power 6 should be 1 mod 13. It's not difficult because 3 to the power 6, it's like 3 cube square. 3 cube is 27, which is 1 mod 26 or 1 mod 13. Okay, so you can clearly see that we can directly check 31 is a pseudoprime to the base 3. Okay. So earlier we showed that to the base 2 there were infinitely many pseudoprimes, but in fact we can show it for any base, and that has been given as a problem in the practice set, which I have uploaded. Anyway, I'll show you the problem set. Okay. And what we what we'll be doing, like next week, we'll discuss these problems. Okay, so you try to work out the problems from both the problem sheets, and whatever your difficulties are on Monday, and if necessary on Tuesday also, we'll discuss those problems. Okay, maybe I'll give some hints, or maybe I'll solve some of them in this class. But those of you who can and evaluation. Okay, so next week on Friday, we'll circulate some forms where we'll ask some questions, and you have to answer within that given time during the class time itself, and that will be our first evaluation. Okay, that will be next Friday. So we'll discuss the problems on Monday. Okay, and then, but on the top of that, when we discuss the problem, suppose you give me some feedback or answers, I'll keep track of that as bonus marks. Okay, apart that will be our regular evaluation. That will be the main evaluation that will circulate as a form, and you'll have to, like, it will be like fill in the blanks or multiple choice, like that, to start with. Okay, so main evaluation will be that. But suppose in this problem sheet, some question I'll ask, and if someone can give me an answer during this live interaction, I'll assign some bonus mark to that, and that bonus mark will come into force like later on. Okay, so at some point of time there'll be some amount of, but it will be just a bonus mark. It is not like your main evaluation, because that way I want to see how you are doing. Okay, normally in normal class time, it would have been during the class hours, I would have asked this and I would have known. But anyway, these bonus marks will be only used to, like this, the grade separation. Because sometimes what happens, 0.5 mark separation is there. Because of 0.5 marks, or because they are like, okay, in this course, there are 180 students. So your marks distribution will be almost like a continuous spectrum. So it may happen, just like it happens in 101 or 102. It will happen to a lesser extent here. But it happens that sometimes when you have 600, 700 students, many will be separated. I mean, it will be like a continuous, like 31, 31.5, 32, 32.5, like that. So they are actually, we have to draw the line somewhere there. Because of 1 mark, some students get a lower grade, BB grade from AB grade. So in those cases, your live answers will count. Okay, your live answers, suppose you have done that will help you in crossing a grade. Okay. So anyway, but in general, for your understanding, you try these problems, and we'll see Monday. And I will also try to see how you are doing. And okay. Okay, so this is Pseudoprime. So there is a natural follow-up. What are the karmical numbers? What are karmical numbers? It's like a strong pseudoprime. What is a strong pseudoprime? I mean, it's just another term I've thrown in. But it means it may behave like a prime, not just to the base 2 or 3, but any coprime base. Okay, any integer a coprime to n you take, and a to the power n minus 1 you take, you get 1 mod n. Certainly, this is true for prime numbers. Okay, and these karmical numbers, they are like strongly resembles a prime. So they sometimes, another standard terminology is strong pseudoprime. Okay, because they strongly resembles a prime number compared to pharma pseudoprime, because they are only base 2, or pseudoprime to the base 3. It is only 3 you are talking about. Now you are changing the base. You are allowing a to be anything less than anything coprime to n. Okay, and still there will be composite numbers exhibiting this type of behavior, and these are called karmical numbers. Okay, for example, 561 is a karmical number. Okay, why it is a karmical number? Let's just see this first. First of all, it's a composite number. It's product of 3 times 11 times 17. Okay, so what do I have to show? I have to show that a to the power 560 is congruent to 1 mod 561 for any a coprime to 561. So let's take any a coprime to 561. So it will be individually coprime to 3, coprime to 11, coprime to 17. Individually it is coprime to all of them. And each one of them I'll apply Fermat's little theorem. So because I'll be interested in A raised to 560. So let's see what happens if I do A raised to 560 mod 3. It's like A square to the power 280. And by Fermat's little theorem, A square is 1 mod 3. So it is 1. What about 11? A to the power 560 is A to the power 10 to the power 56. And A to the power 10 by Fermat's little theorem is 1 mod 11. So this is also 1. And mod 17, again, it is a multiple of 16 also. Okay, so 16 to the power 35, this one. So we can see that any A coprime to 3, 11, 17, which is actually same thing as A being coprime to 561. So it is divisible. I mean, it is A 560 is congruent to 1 mod 561. So 561 is a karmical number. And what is the miracle? The thing is that n minus 1 was divisible by p minus 1. So you see what is the why it works so nicely, because when we had n minus 1, it was a multiple of p minus 1 where p was a factor. Okay, for each prime factor of this number, p minus 1 divided this index. P minus 1 divides n minus 1. In fact, we'll show this later, or one can show, will not show, but maybe you can try. And I have given some assignment problem, I mean the practice problem also. I have given hints how it can be done. Okay. So, but anyway, this is a karmical number. It's a strong pseudoprime. It's not only to the base 2 or 3. In fact, anything coprime to 3, 11, 17 will work. If you take 12, 13, 14, 15, 17, you have to stop. Again, you take 18, 18 you cannot take because it is not coprime to 3. You take 19, 20, okay, 21 and 22 you cannot take, but if you take 23, all these numbers raised to the power 560 will be 1 mod 561. So it's a karmical number. So that shows that converse of Fermat's little theorem does not hold even in a stronger sense, that if A to the power n minus 1 can be congruent to 1 mod n for all integers coprime to n, but does not imply n is prime. So karmical numbers are precisely these counterexamples. Okay. So finally, I'll mention some facts about karmical numbers. Karmical numbers have at least 3 prime factors. Okay, they have at least 3 prime factors. And if you specify 2 of these factors, suppose it's a product of 3 prime factors. If you specify the first 2, then there will be only finitely many which can be the third factor. Anyway, maybe it's not so interesting, but anyway, I've just written it down. But this one is important. Every karmical number is square free. Square free meaning it's not divisible by a prime square. For example, 8 is not square free, or 12 is not square free, because 2 square divides 12. Okay, so a karmical number has to be product of distinct primes. No primes will have exponent. Okay, so square free will always be square free. And I've given it as a problem in the assignment practice set. By applying Chinese remainder theorem, one can simply show this. Okay, I've given this as an exercise. Maybe I've given some hints also. Okay, so karmical numbers are square free. And this result, of course, we'll just mention. We are not talking about proof or anything. That let Cn denote the number of karmical numbers less than n. Then for sufficiently large n, the number of karmical numbers is at least n to the power 2 by 7. So that shows there are infinitely many karmical numbers. Okay, there are infinitely many karmical numbers. Anyway, so for us, this is the one that can be easily proved with Chinese remainder theorem. Okay, so this is okay. So any question? And then I'll show you the assignment problems. Okay, any question? And 341, why it is a pseudoprime? Okay, I'll discuss this. Okay. Yeah. So why 341 is a pseudoprime? Okay. So to qualify as a pseudoprime, what we need, we are saying that it's a pseudoprime, meaning pseudoprime to have base 2. That means 2 raised to 340 we'll have to look at. 2 raised to 340 should be 1 mod 341. Okay, that is the requirement, because it's always better to identify what you want to prove. So in this case, we want to prove 2 to the power 340 is 1 mod 341. And what will be, and of course 341 should not be a prime. So first of all, we factorize this, because it's a small number, we can easily factorize it. So 11 and 31. So we are interested in 2 to the power 340 minus 1. But so in other words, we want to look at 2 to the power 340, but 340 you can view it as 10 to the power 34, for example. When it comes to the prime 11, 340 can be viewed as 2 to the power 10 to the power 34. And what is the advantage? By Fermat's little theorem, 2 to the power 10 is 1 mod 11. So 2 to the power 340 will be certainly 1 to the power 10, 1 to the power 34 mod 11, and that is 1. What about 31? I cannot directly write 340 as 30 times something. So, but still what I will do, I have 2 to the power 30 congruent to 1 mod 31. I will go as close to 340 as possible. I will raise it to 11. If I raise it to power 11, it will be congruent to 1 to the power 11. But 2 to the power 30 to the power 11 is 330. So from 330 to 340, only 10 powers of 2 are left. Okay, so that's what we are doing. 2 to the power 340, we are going in like this. 2 to the power 10 to the power 34, and by Fermat's little theorem, this is 1, so it is 1 to the power 34. Because A congruent to B mod n implies A to the power n is congruent to B to the power n. Okay, A to the power k is congruent to B to the power k mod n. So we have this. What about 31? Okay, I get it as 330 plus 10. What is the advantage of 330 plus 10? Because this 330 can be made to 1, because 2 to the power 30 is 1. So I left with 2 to the power 10. I can directly compute 2 to the power 10 also and do, but better to do 2 to the power 5 square, because 2 to the power 5 is 32. And 32 is, okay, this should have been 31. 2 to the power 5 is 32. So 32 is 1 mod 31. Okay. So let's see, any other question? Sir, can you please use something like pen or pointer kind of thing to write expressions or something? In fact, what I'll do, I will do away with the slides soon. I will be using a live Windows journal. Okay, so it is just a matter of time. Maybe the week afterwards, I'll just use, soon I'll be, maybe certainly group theory, but I'll just do live writing. Okay, I'll not pre-type, so that if you have any queries or anything, I can just write. Okay, so I'll do like that. Okay, because right now I'm using the desktop. So when it comes to, because only 2-3 lectures are remaining for number theory part. After that, we'll go to group theory. And when we go to group theory, then I will start with tablet PC. Okay. Moving the cursor does not work. I see. Okay. Yeah. Okay. So I was trying to move what, yeah, if it does. Anyway, I'll use the light board and let's see. I'll use Windows Journal from group theory part. So what are the remaining topics? Is Euler's theorem, I mean arithmetic functions, Euler theorem, and RSA. If Mn is larger pseudoprime, then why does 2r minus 1 divide 2n minus 1? Okay, I will explain again this one. See, okay, first question is Mn to be called a pseudoprime, Mn should be a composite number. Okay. See, to be a pseudoprime, it should be a composite number first. So here we are showing that it's a composite number. Had it been a prime number, then it will not be a pseudoprime. So first we show this, that it has a proper factor. Proper means strictly bigger than 1 and strictly less than the number. Then, and why it is a factor, of course, I have explained. Okay. Then we have to show 2 to the power Mn minus 1. What happens to that? to the power mn minus 1. In other words, to the power 2n minus 2. Okay, to the power 2n minus 2 is what? That's all. Okay. And as I said, you work it out. And then you'll have the slide and you work it out. Okay, so do we have class tomorrow? As will be following Tuesday timetable tomorrow. Okay, good that you reminded me. So because I did not realize this. Okay, so so you try these problems tomorrow then. Okay, so I've given this. Okay, I'll show you the problems. Okay, sir, can you in the proof of 561 current? Can you explain the last line? Okay, let me explain the last line in the proof. 561 is okay. So where does it go? Okay, sorry, these headings were a bit misleading. I corrected all the typos, but this common heading is already there. Okay, anyway, so this is actually karmical numbers. Okay, so 561 is a karmical number. Okay, so last line. Okay, see what I'm saying is that a to the power 560 minus 1 is divisible by 3 and by 11 and by 17, and these three are co-prime. So if you look at the prime factorization of a to the power 560 minus 1, 3 will appear, 11 will appear, and 17 will appear. Okay, and appearance of one does not affect the appearance of other. In other words, they are co-prime, pairwise co-prime. So if 3 is occurring, 11 is occurring, and 17 is occurring in the prime factorization of a to the power 560 minus 1, then all 3 will be there. Okay, so in other words, a to the power 560 minus 1 will be divisible by 3, 11, and 17. Why it is so? Because they are co-prime. Otherwise, what would happen? It would not matter otherwise. Like suppose this is 3 and this is 9. Then you cannot say that it will be divisible by 27. Okay. But if it is co-prime, certainly you can. Any other question? What is the syllabus for first evaluation? So whatever we covered up till now today, okay, that is the grading is relative or absolute. That we'll see as we go along. Okay, but yeah, absolute grading we hardly follow. So, but yeah, so yeah, it cannot. I mean, no, it will be unlikely to be absolute. But anyway, we'll see that. Also, we have to wait for the guidelines. Okay, it's not like our individual decision. So, CNET as it directs us, we'll see. Okay, because as all faculty members discuss and suggest and all, so since it's a new scenario, I mean, so we'll abide by CNET guidelines. That's all I can say. Okay, so tomorrow is Tuesday timetable. So 12 to 1. So you work out the problems. Okay, maybe tomorrow we'll mostly focus on the first problem sheet. Okay, or if you're fine with it, if time, I mean, we have more time, we'll consider the second one also. Okay, let me show you the, okay, you see I've uploaded it, but let me just practice it. Okay, so these are the problems. Okay, some of them are just direct questions. Let's solve the linear Diophantine equation like this. It's direct. Linear congruence, it is direct. This is just Chinese remainder theorem, direct. Okay, that it leaves remainder this. Okay, there are here are okay. So this t is missing, so that there are infinitely many positive integers which cannot be expressed as sum of 3 squares. Because see, this is a historical problem. I mean, connected to the historical problem. Okay. The historical problem is which numbers can be written as sum of 2 squares, okay, or more elementary level, which primes can be expressed as sum of 2 squares. For example, 5 you can write as 2 square plus 1 square. 17 you can write as what? Sum of 2 squares. Can you suggest?
4 square plus 1 square, sir.
No, 1 you don't, okay, fine. 4 square plus 1 square is also fine, yes. Okay, so that you can always do, but you'll not be able to do so for 23. Okay, 23 you'll not be able to write as a square plus b square. That is easy to see actually, by the way. That 23, okay, any prime which is 3 mod 4, you cannot write as sum of 2 squares. But converse is also true. that if it is 1 mod 4, you can write. I mean, if a prime number is 1 mod 4, you can write it as sum of 2 squares. Anyway, but sum of 2 squares do not cover all the integers. In fact, sum of 3 squares also do not cover all integers. But sum of 4 squares cover all. Any integer you take, you should be able to write it as sum of 4 squares. 4 squares of integers. That is famous theorem by Legendre. Okay, 4 squares suffice. And there is a general Waring's problem that whether any integer can be written as say these number of cubes and these number of fourth powers and these number of fifth powers, these number of kth powers. Okay, that's known as Waring's problem, and that also has an answer. Okay, you have to take sufficiently large number of terms, then every integer should be expressible as sum of kth powers. But anyway, this problem is much easier. Okay, and then we're showing that there are infinitely many positive integers which are not representable as a sum of cubes of two other positive integers. Okay, sum of cubes also do not cover all integers. They leave out infinitely many. And this is like some special case of Fermat's last theorem for index 3. That x cube plus y cube equal to z cube, and 3 does not xy, it does not divide xy z, it has no solution in integers. Okay. And this one again, that this number is a perfect square if and only if n is 3. Okay. And these are just congruence problems. Okay, this I already did probably. Anyway, this is just a practice. Okay, this I already spelled out in the class. Okay, this in fact I showed that it's a karmical number. So for to the base 2, again same argument will work. And this is to show that it's a karmical. So these are almost direct questions. And when I say that karmical number must be square free, using Chinese remainder theorem you can do. And this property that if you take a composite square free number such that pi minus 1 divides n minus 1, that this number is karmical. Okay, and that this number is also karmical number. Okay, and this is a proof that there are infinitely many pseudoprimes to any base a. So to any base a, you can prove existence of infinitely many pseudoprimes to that base. Anyway, hints are given. So try this. And again, so yeah, these are the problems. Okay. So as I said, problems use congruence and Chinese remainder theorem. Maybe I should have mentioned, but congruence covered Chinese remainder theorem and Fermat's theorem. Okay, that's all. Okay, so you look at the problems, and as I said, we'll take into account your live feedback. Live feedback meaning if you can answer some of the questions. Of course, some of them are very direct, so so those answers will not count for much. Will not count, but yeah. But largely will be just what we circulate. That's the main evaluation. Okay, these are just like tiebreakers. Okay, this question answers that you have that can be tiebreakers when we find difficulty in separating the grades. Okay, grade separation. Okay, so any other question? Can we have practice problems and discussion on Monday? Okay, fine. If that is what you want. Okay, so if that is what you want, then we can do that also. Then tomorrow we'll have some. But yeah, is that more of you want? I don't want to see. Okay, how many of you want it on Monday? Practice it. Okay, so probably more of you want it on, I mean, not, okay, so, okay, fine, we'll have it on Monday. So tomorrow we'll have some class. Okay. But the Sunday do we have a scheduled class? Because I have some other things. Okay. Any other question? Okay, so that's all I suppose.